Yeah, so let us begin. Um, Sorry, I think I opened the slides. Yeah. Um, did you all receive the mail about the lab being available? Uh, has anyone tried using the virtual lab? Tried out anything? So I received a mail on, I think, Thursday or Friday that the lab is now available. So I just wanted to confirm if you all also have received any similar email, and if anyone got any chance to try something out on those email labs. So what I'll suggest is we will have a theory session today, as in discuss the map reduce framework and what this programming model is about. And next week we we will spend the lecture hour trying to do some hands-on with the available labs. Okay, so if possible, you all try out your login, check how you can log in, what is available to you. If not, better write an email to the team and at least log in and check, and maybe run up one OpenMP code or something and try it out. So next week, then we can do some hands-on session in that lab. Still, I also need to check my credential and how things work. So I will also try to see and then announce on the Conta accordingly. How are we going to go about this next week's class? So yeah, and I hope everyone has answered mid-semesters. The makeup and the main exam both have happened. Most of the evaluation is also, I think, complete. For at least the first cycle was complete. I'm not sure about the second cycle. So yeah, so let us move on now. In the last class, we talked about scale out redundancy. Anyone would like to tell us like what did we discuss? What was it about? So in the if you recollect last class we discussed about um, you know scale out, which is called as horizontal scaling, which is a strategy of increasing systems capacity where we add more machines to a distributed network. So the goal in that is to handle more workload, like more users or more data. How do we do that? Is by we divide the work among multiple resources, and we also talked about client server method, distributed P2P, if you all recollect. And we also talked about the redundancy, that is fault tolerance. Why we need fault tolerance is if we have duplicate critical components or data within a system, then if one fails, we have identical backup which can immediately take over. So through this, we achieve high availability and fault tolerance, which ensures that the systems all are always operational despite if there is any component which fails. So, so let us now move on to what could be a programming model that could be, that can be used for with this scale out or a distributed system. So the model could be a MapReduce framework. So in this, now what is MapReduce? Anyone has used MapReduce? Who wants to? just give an introduction or talk about it? Okay, so I assume you all are freshers in, and we all are trying to now explore what this programming model is and why do we really need this programming model when we have already you know, discussed about OpenMP, MPI. In the later classes, we will also talk about CUDA. Then why do we need this MapReduce? So the motivation is, if you in the classical data processing, you have a CPU, memory, disk. In case if data fits into the memory, what we do? We load data from disk to memory and then process from memory. If it does not fit into the memory, we take part by part data, take it to the memory, process the data, move it back to the disk, right? But what happens when we have huge amount of data, such as 10 billion web pages, with average size of web pages around 20 KB, so total is around 200 TBs of data. The disk read bandwidth is only 50 MB per second. If we try to store 200 TB of data on one disk and try to access it at the bandwidth of 50 MB per second, what will happen? We will the time to read this much data will be almost 40 plus 6 plus days. And imagine a web browser, you are trying to access some data for, and you're trying to access something, and imagine that browser is giving you that output after 46 days. We cannot practically have such systems, and having these systems, a single system will not work out. We have to have a distributed work. So we can distribute this work across hundreds or thousands of machines, which will then bring down this days to hours and to minutes. And that's what we kind of achieve using something sort of a MapReduce. So MapReduce is a simple programming model. Well, where what we do is we are able to hide what are the difficult parts. That is, how do we split the data among different machines, schedule, how failure recovery happens, how we sort data, how we aggregate data. All this is taken care of by a simple programming model. So here, what we do is we use multiple interconnected machines, and what they do, how do we do it? We take a big data, a lot of data, and then we split this data. Now, this split data, that is, that splitting is what we call as chunks. This data is then sent to different machines and processes, and different machines and processes will then do the whatever task it needs to do, and then the data is collected back to a from these multiple machines to a single machine. And this is what the distributed data processing cluster computers will do for us. Now, what are the challenges when you have a cluster computing scenario? Nodes can fail. So, if you have a single server, the single server lifetime is around 1,000 days. So, 1,000 servers in a cluster, so one failure per day will happen. So if we have 1 million servers in clusters, 1,000 failures a day can happen. Now, what will happen if a node fails? There will be data loss. And what if this node fails in the middle of a very long and expensive competition? We will have to restart the whole competition. So the performance get degraded significantly with this. What are the other challenges? That could be a network bottleneck. So if we have a computers which are like exchanging data through a common network, the network bandwidth is very, very critical. For example, if you have a network bandwidth of around 1 GB per second, if you want to move 10 TB of data, it takes 1 day. So imagine the amount of time it takes as the data that we need to communicate amongst a cluster of networks increases. Now, why do we need MapReduce? We have already learned MPI, right? And there we saw that we can have multiple nodes, and these nodes can communicate, send, receive data, do the task. But then why we need a special programming model when MPI exists, which is meant for distributed computing? Because the fact is, MPI or distributed programming is not that easy. It is hard. And why it is hard? Because data distribution across machines is a very critical part. And doing it manually, taking care of everything, programming it every time is not easy. We want to ensure that all machines have roughly the same load. So taking care of this scheduling of data, assigning of data is also a very critical task. When there are multiple machines involved, avoiding race conditions is very, very critical if you do not want your results to get hampered. And it is again a very, very difficult task, because if you have, say, two tasks, T1 and T2, as we know, in race condition, correctness will depend on what is executed first. So when there are multiple nodes working on a common computation or trying to solve something, how the results are collected or how the results are then considered for the final computation or whatever will be very critical, and programming this is not a easy task. So in general, distributed programming is hard. So if we can have a simpler programming model which can work from multiple tasks, that would be a really useful approach. So what is the solution to this problem? Yes, the topic of our class, today's class, that is MapReduce. MapReduce is a programming model or a framework which processes large amount of data in parallel across many computers in a cluster. You all know who introduced MapReduce? Anyone has any idea about it? Around what time it was introduced? So MapReduce programming model was introduced by Google engineers Jeffrey Dean and Sanjay Nimawar. They provided the details of this model in a white paper which was published in 2004. Yeah, someone is saying something. So this paper, I have provided a link in the data slides. This paper provides you the details of how Google uses MapReduce internally to process this massive amount of data which is generated by the web indexing and search operations, and how it provides the foundation for the distributed big data processing frameworks that you know then were created after MapReduce. So one of the very popular one is a Hadoop MapReduce framework. So when you have terabytes of data, we cannot have, as we say, as we've discussed this multiple times now, it's too large for one machine to handle this. So how do we go about it? We split the data across multiple machines. We process each part in parallel and then combine the results efficiently. And as we discussed, manually handling this, that is data partitioning, scheduling, communicating, then fault tolerance, is complicated. MapReduce hides this complexity. It lets you write only two simple functions. First one is map and the second one is reduce. And then the MapReduce framework takes care of everything else. You just have to provide these two functions, map and reduce. All other things are taken care of by the framework. So for this, we need a distributed file system, which is, where all files are part of one logical file system. You don't have to, know physically which machine holds a chunk of data. So uh, you can have, a common path where you feel like the data is stored on one of the machines, and then it is take, this will the map reduce will take care of how to automatically locate where each piece of the data is located. So what you need to do is each data that you need will be replicated across multiple copies. We will see that. And why we need to do this is, if one node fails, then MapReduce can rerun the map task on any other node, and then get the replica of the data. And this will ensure that there is enough fault tolerance and high availability. So as I mentioned, data is kept in chunks. It is spread across machine. Each chunk is replicated on a different machine. This ensures that the data is there, persistent, and fault tolerance. So for example, we have two files, A and B. We have three computers. A and B can be divided into A can be divided into three chunks. B can be divided into two chunks. These chunk servers that we have, three computers, can store data in this fashion, where A1, A2, A3 can be on one machine and B1 can be with them. In another machine, B1, A1, B2, and A2 can be there, and A3 and B2 can be another machine. So every chunk of data is replicated on two of the machines. Chunk servers also do the computation. They are not just meant for storing the data. Uh, Sorry. Uh, can we let us take a 5 minutes break? I'll be right back. Okay, so let us continue. Yes. So as we discussed, we need chunk servers. So the distributed file system in a MapReduce looks like we have a chunk server where we split the files into contiguous chunks. It could be of 16 to 64 MB. Each chunk is replicated usually two times or three times. And you try to keep these replicas in different racks, not on the same rack. There will be a master node which will be which will have the metadata about where these files are stored, and you might also replicate this master node for fault better, avoiding fault tolerance. So this is the white paper on MapReduce, which if you are interested you can go through and learn more about how MapReduce works. Now let us uh, discuss an example of MapReduce which is provided in this white paper. It's a very simple example. So the example could be counting of words. So let's say we have a huge text document and we want to count the number of times each distinct word appears in this file. The sample application could be if you're trying to analyze web server logs to find what are the popular URLs. How can you solve this using a single machine? So if you see here, so the input file, there are two input files. Now in MapReduce framework, how things work is if the first input file is this is an apple and second is apple is red in color. These are two different mappers. Each one will first calculate the number of times each word is repeating. This is an apple. Once each word is repeating, and similarly for the second. Now, in the next stage, there will be a shuffle. In shuffle, what happens? Each word is sent to the node where it belongs. So here, this is only once. So one is twice, N is once, apple is twice, red is in once, in color once. Now you will do the reduction. In reduction, you calculate the count of how many times the word is repeated. Once you do the reduce phase, in the next phase, the output file is generated where you get each word and how many times it is repeated. This is a simple example of how the MapReduce framework can get different input files. Once they get different input files, it maps these inputs. Then there is a shuffle that occurs, and after the shuffle, it is reduced, or whatever computation needs to be done is done, and then output file is generated finally. So why this example captures the essence of MapReduce? There could be a case where file is too large for one memory, but all words and count pairs can fit in the memory. So you can create a big string array or you can create a hash table. In case 2, all pairs do not fit in memory but fit into the disk. So how do you do that? Is you break the text document into sequence of words, sort these words. Once you sort these words, the words will come together, then count the frequency in a single pass, and then you reduce you know, get the final count as the output. So, for this example, getting the words is mapping where you extract something you care about. Here we are focusing on word and its count. Then you do the sort and shuffle. That is, you sort and shuffle based on common words you put together. Once shuffling is done, you do the reduce. You aggregate, summarize, and then save the results that you want. That is the word and the count. So this outline remains the same across multiple problems of multiple domains. Map and reduce is what you define to fit the problem. What should be mapped and what should be reduced is what you need to define. So the map step is where you have input and key value pairs. An example could be file name and its content. In this case, F1 is the file name, C1 is its content. Then you create intermediate key value pairs. It could be word and count for each file. Each word and count. K1 is the key, V1 is your count. The next step, once you have the keys and the count, is group by the key. Group by the what is the word. So that you do. So now each key, how many times it is repeated, you get the V1, V3, V6, which are the count for respective keys in different files. Then V1, V3, V6 you combine. You might want to count, you might want to find the max, or whatever is the function that you want to use for reducing. And you get key and its value pairs in the reduce phase. So let us again take the same example. If we have a big document, the crew of the space shuttle Endeavour recently returned to Earth as ambassadors and harbingers of new era of space exploration, crew members at, and so on and so forth, whatever. A big document. The next step would be where the programmer will provide what should be the mapping function. So if the programmer is saying read input value and produce a set of key value pairs. So you create key and its count, as you can see here. Next, the MapReduce framework will take the group by key, collect all pairs with the same key, crew, space, the shuttle, that way. You separate out and combine what is common. That could be like a sorting phase here. In this particular example, it will be a sorting. Then programmer will also have to mention what should be the reduce function. If the programmer is saying collect all values belonging to the key and the output. Since crew is repeated twice, crew comma 2, the is happening thrice, so the comma 3, shuttle and recently is 1, so it is 1 1 each. So as you can see, a big document could be divided into 3 chunks, then 1 to 3 mapping functions. Then these 3 can be combined again, shuffled, and then finally reduced. Sorry, and we get the output. So you need a map function and you need a reduce function. So we'll see how mapping and reduce can be done with the function. This is a pseudo code. Here we are providing the mapping function. For each word W emit W comma 1. Here for each count V it values, result is summation of all the V's. That is reduction. That is counting the number of times a word is repeated. So, so here is how it will look. The map task will be done by the by first phase. Then the data will be shuffled. You will sort and group. After shuffling, then the reduction task will happen. That is R, and you will get what is the reduced output. So, as we have mentioned, programmer's responsibility is designed in two functions: map function and reduce function. But there are two important issues that you need to note. Since the not, network is a bottleneck, you should ensure that however the way you design your problem, you should minimize the data communication across different machines. So, which are the problems which are suitable for MapReduce? MapReduce is suitable for batch processing, where you have data which is which can be updated using multiple can be divided into chunks and can be updated together, like whole batch of data can be processed together, because the mappers do not need data from one another as long as they are able to do whatever the mapping that needs to be done for their particular data set on their own. Example, as we've seen in word count, we'll see more examples later. So in general, if the problem can be broken into independent sub-problems, MapReduce is a go-to solution for you. If the problem cannot be independent, MapReduce will not work. So what are these not suitable problems for MapReduce? So in general, when machines need to exchange data often, it becomes a problem because network becomes a problem. So applications will require very quick response time, like IR, but query processing is not suitable for MapReduce. Machine learning algorithms require frequent parameter update also are not suitable for MapReduce. So some examples could be that a matrix addition. Can this be done using MapReduce? Yes. What is the map function? Key will be the row number. Value will be elements of row. Right? You can divide a matrix into key to be the row number and values will be the elements of the row. What will be the reduce function? For each key, reducer will have two arrays. Hence, reducer will have to add the two rows. Right? This will be one example how MapReduce can be used. Another example could be, can you compute the natural join? That is, combine rows from T1 and T2 such that rows have common value in column B. Can this be done using a join? So what will happen? The map phase, in mapping phase, what will we do? You know, in this phase, the mapper will read all the records from dataset we joined, and it will create some join key, right? For example, a customer ID for each record. Then it might create a composite value which will include the original record plus a tag to identify which what is the source table for this. So the key could be a join key, and the value could be a source tag, and the data. So if you, let's say, if there is an example, if you are trying to use join customer records, so customer, let's say customer number is 101 and customer is Alice, and his order record is 101 because customer ID, and he is trying to order a widget, then the amount that you spent in this widget. So your key will be customer ID, your order, and the amount. Then what you will do, you will go to the shuffle or sorting phase. Here, the map reduce framework will automatically collect all the intermediate key pairs, and it will join the same key and send them to the same reduce instance. So the key is 101. So all the values of 101 will be shuffled. The reducer will receive the join key and which will complete all records associated with the key. That is, it groups the records based on what is the source tag, that is the customer, and what is the order. So it will perform, a join where it will combine the record from the source list and produce the final join record. So you can think about it how you can, there are very interesting, problems where you can understand how joins in MapReduce work and how joins in MapReduce help you to get the data faster. So real life examples could be search indexing, that is Google Search 22. It uses MapReduce. Log analysis, if you're trying to assess or analyze some logs. Inverted index building, word frequency, trend analysis, large scale machine learning, pre-processing specifically can be done using MapReduce. When not to use, as we have mentioned, MapReduce is great for large batch style data processing, but it's not a silver bullet. Like there are situations where it is inefficient or unusable. So it could be, as we discussed a few earlier, an iterative algorithm. That is, for example, if you're doing machine learning training, what happens when many machine learning and graph algorithms, what they do is specifically examples like gradient descent or PageRank or k-means, they're iterative. They need to repeatedly process the same data set and update results each time. So what will happen in MapReduce is each iteration will write intermediate results to the disk and then read them back for the next iteration. So that the constant disk input output and job restart overhead will make it very slow for any kind of iterative workload, if there is any iterative workload. There are other frameworks such as Apache Spark, which keep intermediate data in the memory across iterations, so they are much faster for ML and graph processing kind of examples. So for example, it could be that if you're trying a model over 100 iterations, MapReduce will perform these 100 separate jobs. Each will read data and write data, terabytes of data. But in Spark, Apache Spark, you can cache this in RAM and you can reuse it. Another place where it can be used is real time or streaming data. So, uh, as we have seen, MapReduce is designed for batch processing. That is, large data set that are already available to you on the disk. It is not meant for any continuous data streams like live sensor feeds, log streams, or financial trick data. For real time or near real time analysis, you need frameworks that can process data as it arrives. Like there are some other frameworks like Apache, Kafka, Storm, or Flink. These systems maintain long running processes that continuously react to new data rather than starting a new job each time. So, if, for example, if you want to monitor trending hashtags on Twitter in real time, MapReduce will not be a good option because by the time the job will finish, the trend will change. It does not exist. It does not remain. Trends keep changing. So MapReduce may not be a good choice here. The third one is where you have small jobs. So, uh, say each MapReduce job has a significant startup overhead. That is, starting takes a lot of time. So, the framework must schedule tasks, set up containers, manage splits, and handle coordination. So, for small data sets and or short computations, this overhead dominates the actual work. It is like you are trying to use a bulldozer to move a flower pot. It's not needed. It works, but it is you're wasting a very important critical resource. For small or iterative jobs, you have much better other approaches that you can use. So in short, MapReduce is excellent for large batch oriented data processing where latency does not matter much, but for iterative real time or small interactive workloads, newer frameworks like Spark, Flink, or Kafka are much better suited than using a MapReduce approach. So we'll discuss how MapReduce works with Hadoop. Before that, maybe we can take a 10 minutes break and come back around 9:20 and then discuss Hadoop in MapReduce. Okay, let us continue. So MapReduce, we've seen what MapReduce programming model is, and there are multiple implementations of MapReduce. One of the very popular implementation of MapReduce is using Hadoop. So MapReduce is used with Hadoop framework, which is used again for processing massive amount of data. This data processing happens on large clusters of hardware, and with this, we can allow the applications to store the data using distributed form, process large data sets across groups of computers using some simple programming models, and we can then get aggregate the data into you know into multiple nodes. So it's a open source implementation which was first developed by, as I mentioned, Google's MapReduce and Google File System. It consists of two components. The first one is HDFS, which is Hadoop Distributed File System, which we use for storage, and then it uses MapReduce for programming and execution framework. Together, these two help you to store and analyze terabytes of data or petabytes of data very efficiently. So how it works is, so the data is stored into HDFS, split into large blocks. Could be an example could be 128 MBs each. Then there is MapReduce framework, which launches the map and reduce task, which is done close to the where the data is stored. Results are then returned back to HDFS. So data will stay in place, computation will move to the data, and this is what is the key principle of Hadoop. So it uses three components: HDFS for distributed storage, Yarn for resource management, and MapReduce for computational layer. So you will need what is the node name or data node. You will need a resource manager, which is like Yarn, and a job tracker or task tracker. So let us look at the same world famous example we've seen so far, which is word count, where each mapper will read lines of text, breaks them into words, and emits word comma one pair. During the shuffle, all pairs with the same word are grouped together. So this purpose of this mapper.java that you're seeing here is to read the input data file line by line from your HDFS, process each line to generate intermediate key value pairs, and then in word count, the key is word and the value will be 1. So here, the extends mapper that you see will is will define a mapper with input key type object, input value type text, output key type will be text, and output value type, that is int writable. So this method will be called once per input line. Then you take this value, you read this value, you split the words using this line, split value dot split. This will split the line into word context dot write, where each word will be generated. So emit each word with a count of 1. So every word will be created and it will be set to count of 1 in key. Then the programmer has to write the reduce function. This reducer.java will sum all the counts for each word and it will write these two back to the HDFS. So here we are seeing how we can express this data parallel problem easily using a MapReduce. So the purpose of this function is we receive all the values for the same key, which is grouped by the Hadoop. Then we aggregate this value to produce a final output, which is key value pair. So in the word count example, what we are doing, it sums up all the ones that we have we had created in the map function, and summing up all the ones will give you the count. So now the purpose of this reducer.java is receive all the values for the same key, aggregate the values to produce a final output key value pair, and in word count it will sum up all the words, right? So here in the extends reducer takes the input key type, which is text, list of values, which is int writable, output again we expect it to be text, and the type is in text writable again. This is called once for every key with all intermediate values for that key which are given to int writable. Now here we will iterate over all the ones in the word sum, right? And then we will accumulate the total count by using the sum function. And this will write the final word back to your HDFS. So, uh, can you think of any other example, like other than word count, and how will be the MapReduce function? Anyone? Okay, let us take an example where we are trying to calculate the average temperature by year for a massive data set of weather recordings. Okay, so what is the job here? The job is to process a huge data set of raw weather logs and compute the average high temperature recorded for each year. Okay, so let's assume the input data consists of billions of lines of records in HDFS.
Then your screen was of reducer.java page.
Okay, no, that's fine. I'm just discussing an example. So
Okay.
yeah, you can. So I do not have a slide for this. I thought of just discussing another example other than what we discussed. If you have want to suggest any other example, you can suggest, or we will. I'll talk about the example I'm talking about, where we are trying to process a large data of billions of lines of records of weather data. Okay, so yeah, so first let's assume this input data is billions of lines of data, and each record will contain, let's say, some fields, like it will have a year, it will have the month, a day, and the temperature. Okay, so every record in this line will have a year, month, day, and temperature. Okay, so what should be the MapReduce function? The MapReduce function has to, extract some useful information from this. So the goal of this mapper is to isolate the data we need and prepare it for some grouping, right? So the logic could be that this mapper function will read each line, it will extract what is the year, and it will consider year as the key, and it will output a pair which will represent how many times this temperature is observed in that year. Okay, so the output is year, temperature, and count. Okay, so the input records, as I mentioned, let me write so that will be, say, 2023, seven is month, then date is 15th, and let's say temperature is 32.5. Okay, so these are all the input records. Hmm? So now mapper function, what it has to do? It has to now create the keys. So we are dividing or designing this mapper function so that what is expected from this mapper function is it has to create keys, where the key should be, so map E1 and V1 should be list of year, the temperature for that year, and 1. Okay, so for every input record, for this input record, what will be the key that will be created? Will be 2023, comma 32 point, and the value will be 32 point comma 5 comma 1. Okay, next phase will be shuffle and sort, that is grouping. So the input will be now grouped according to the key. So here, after shuffling, what will happen? All 2023 records will be in one place. All 2022 records will be in one place. or 2024 records will be in place, 2025 records will be in one place. Okay. Next we have to reduce. So reducer will take this data for a single year and it will perform some final calculation. So it could be that the reducer loops through the list of values. It calculates the sum of temperatures and how many total readings it has, and then computes a sum by count, which is the average temperature of that year. So the reduce function that you are developing is, let's say if whatever data we have, the sum here is, let's say 63.5, because the data has a count of 2 per year. So average will become 31.75. So what have we achieved through this? So instead of a single server trying to go through billions of records sequentially, MapReduce is allowing thousands of mappers to concurrently calculate the sum and count for all these small data chunks, and the reducer will only have to perform the final small aggregation step for each year, and hence the entire job becomes in minutes and not in hours. Okay, so this is another example of how you MapReduce can be used. So Hadoop is built for large clusters where there will be frequent node failures, right? So what should we do when we have these frequent node failures? So if there is a mapper reducer which fails, the task is to simply rerun whatever the competition it is supposed to do somewhere else. Data is replicated, so the same block exists on multiple nodes, so we do not have to worry about it. Also, Hadoop tries to schedule tasks where the data already resides. So, hence, because of local processing, tasks which run on nodes where the data is, this minimizes the network usage and it also maximizes the throughput. And hence, it becomes a key to scalability. So, in order to wrap up, what we have seen today is Hadoop uses MapReduce, which gives us a powerful framework which lets you process huge volumes of data efficiently and reliably. There are three pillars on which Hadoop is based: HDFS, which is for storage. That too, it is distributed storage when we divide the data into chunks. We use MapReduce, which performs the distributed computation. We use this yarn, which is for taking care of the resource management. But the real magic that you get for MapReduce lies in its simplicity. You only define two functions: a map function, which will run in parallel or chunks of data, and a reduce function that combines these partial results. Hadoop automatically takes care of splitting the data, scheduling tasks, shuffling data between stages, and handling the failures. Because of this design, it enables organizations like Google, Yahoo, even Facebook to process petabytes of data efficiently. However, Hadoop MapReduce is best suited for batch jobs, those where you can tolerate some latency. If you want some real-time analysis or some iterative ML training, you better use newer frameworks like Spark, Flame, or Kafka, which are better options. Having said that, Hadoop still remains the foundation of the big data ecosystem, and many newer systems were built on top of the idea of this MapReduce and Hadoop. Hence, I would highly recommend you all to go through the white paper link that I've shared in this PPT, see how the idea was proposed in 2004, and uh, try to read more about how what are the other different applications other than what we have discussed in this class today, can utilize the Hadoop framework or MapReduce framework to solve the problems efficiently. And as I mentioned in the beginning of the class, in the next class, we'll try to utilize the lab that has been provided now. I request you all to try to log in on this. If you are not able to, try write an email to the uh, you know the web section, get it sorted, and let's try to do some hands-on in the next class. Any other doubts? Any other questions about Hadoop or MapReduce?
So, ma'am, hello.
Yes.
So the map reduce
Hmm.
framework that we can only use with Hadoop, or there is any another use case also.
Hadoop is one, okay, because MapReduce is an idea which was developed by Google. So Hadoop implementation is popular because it's open source, but it is there are this Apache Spark also is successor to what the MapReduce implementation is. So, or even there is Apache Test, which is also available. So uh, there are like there are other implementations which are loosely based on MapReduce uh, concepts.
Okay,
So
ma'am.
Hadoop is the most popular approach. So the Google has its own proprietary MapReduce, which is not open source, but they've
Okay,
explained that idea in that white paper.
but you
But Hadoop became
yeah you
open source. Hmm.
yeah you
Yes.
earlier mentioned that we can use MapReduce with Apache Spark and then Apache 1 or something and the and Apache Hadoop. So all these are managed by Apache, right? So there is
Yeah, yeah,
no.
yeah.
Okay.
Because Google has not made their MapReduce open source, so they have their own version of MapReduce, not open source. And it's not that Apache is the only one who has MapReduce solutions, but uh, because MapReduce is generic programming paradigm, so you can implement it by the way you want. But uh, what happened was since Apache provided a very uh, useful or which could be easy open source implementation, it became popular. That's it. And since Apache is the home to most famous open source implementation, it became like uh, Hadoop became a synonym to MapReduce. That's why. So there are other open source projects as well. Um, there is a complete Python implementation, and uh, there is another uh, open source implementation as well, something like HPCC. Anyone here has used any MapReduce implementation or has used Hadoop for any other example? You can just tell us about your experience or what kind of problems you looked at using MapReduce, if anyone has.
Yes, ma'am. We have used in a company, but it is for storing the data in SDFS, not for the programming perspective. So knows the
Okay,
Storm and Kafka, and then Apache Hadoop, and like the component was known, but not at the programming level.
okay. So you used HDFS just to organize your data, right? In terms of
Yeah, yes, ma'am.
MapReduce was not used. Okay.
So, ma'am, next Saturday, Sunday there is Diwali. So do we have lectures on this day?
Mm, at least I'm told that there is a class. You had received the schedule earlier, right? So the Diwali is on Monday, right? So the
Dhanitra
class
on
will happen.
Saturday.
Yeah,
No,
but
I'm checking.
you can check the schedule that you might have received prior. I think uh, there is a class. Yeah, 18th there is a class. I think we have 7 classes remaining before the company. So let's try to do some hands-on and then we can continue with learning about GPU programming using CUDA. Okay, if there are no more doubts, we can stop here. If there are any doubts, we can stay back and we can discuss.
Ma'am, I do have one question. Maybe I joined late. When are we going to get the EC2 marks?
Uh, the midsem one, did you
Yeah,
answer the makeup or the first one?
first one.
Uh, okay, I will check with the TA. She had told me that she has finished the evaluation, so I assume the marks are available to you all now. I will check with her.
I haven't got it that way.
Okay, I will check with her. She has finished the evaluation that I'm aware of, but I don't know why the marks are not available to you. You have checked using Metal or where are
I
you
checked it
checking?
in. I'm checking in the e-learning portal, my course, and then going to the introduction to the parallel, where I'm getting the quiz marks. The
Grades.
same place.
Okay. No, I think these marks. Okay, I will check and I'll maybe do the announcement on Conda.
Okay, okay.
Yeah. So you were not asked to check it on metal, right? Where the we evaluate the metal portal.
Uh, we we haven't got any notification where to check it. I'm checking it the place where I'm getting the marks for the quizzes. I thought it will come there only, but I haven't got any subject yet.
Okay, but it's okay. If you have answered in the first round by now, all the deadlines are. I think most of the deadlines were over. So I will check. Yeah, and I'll do the announcement.
Okay, okay, okay.
Hello, ma'am.
Yes.
Ma'am, actually, we could see some document has been uploaded in Taxila with the name as assignment one. Can you please brief about it? Like whether
What?
are we, there was a document in Taxila which is
Hmm.
mentioned as assignment one. So, are we supposed
So
to? Yeah. Can
no,
you?
those were the practice problems. Last time students had asked me if they can do some problems so that they can learn more about OpenMP, MPI, what hands-on they can do. So I had shared the kind of assignment problems I give on campus. There is no assignment component for you all, for at least as per the handout. So there is no assignment here, but this is for those who are interested in learning more about OpenMP and MPI.
Okay, got it.
Based
Thank
on
you.
your yeah, based on your time constraints and your interest, you can pursue. There will
Sure.
be no
Thank you.
evaluation.
Okay.
So, ma'am, you are not going to give the assignment. Every subject we are getting the assignment.
At least this course, I did not. Let me just verify once in the handout if they have mentioned any assignments. So there is quizzes assignment here. So uh, so I was supposed to put up a quiz again. If you want me to put up assignment, I can. That's not a problem. You think the assignment is
A-
better or quiz is better?
anything is
And
fine, but I think
also I did not yeah go for any assignments. Yeah, assignments because of the heterogeneity of the group. I I was told that not everyone is comfortable with C and all. That's the reason I went for quizzes.
that's fine, ma'am. I think quizzes is also
Hmm,
fine.
hmm. Those who are interested are familiar with C are wants to try out things. They can yeah they are welcome to try those things. I'll in quiz two. I'll try to ask more programming kind of questions so that it gives you flavor of lab by keeping some extra time for if you want to implement and see.
But ma'am, the EC1 total marks will be of 30 marks, right? So the quiz one was
Yeah.
taken for 5 marks only. So quiz 2 will be
There are
taken
two
for.
more 10 marks again, and there would be quiz 3 again. I Yes,
Okay, so
there will be three quizzes.
there will be three quiz, each carrying 10 marks. You mean, right?
Yes, yes, yes.
Okay. Okay. Thank you.
EC1 can be either two assignments or three quizzes. That's what the guideline is as per the handout.
Okay. Okay.
So I'll announce the quiz next week. I'll put the announcement on Conta, and I'll also check with the team, and I'll let you all know where you should check for your marks. Any other thing? Sure, I'll upload the PPT now.
Thank you, ma'am.
Yes, thank you.
Yeah. Thank you, ma'am.
Yeah, thank you. Thank you for joining. Hoping to see you all in the next class. I understand there is Diwali, but yes, there is a class.
Okay.
Sukanya, anything?